Okay, here we go for the video lecture for chapter 3. For this, you're going to want to have read not only chapter 3 in your book, but if possible, not have to, but if possible, please read chapters or labs 1 and 2 in the lab book that I've provided to you in the classroom online. So, today we're going to be covering matter and minerals. So, these are the basic building blocks that make up the rocks that we are going to be looking at throughout the course of this class. So we need to understand those basic building blocks, the minerals. In order to understand minerals, we're going to have to understand matter, hence why we're going to cover both. So let's start out first and foremost by defining what is a mineral. A mineral, generally speaking, has to meet five qualifications in order to be considered a mineral. First and foremost, it must be naturally occurring, i.e., it needs to form in nature. So, diamonds are a mineral, mostly. If you get a faux diamond or a fake diamond, a man-made diamond, technically that's not naturally occurring because it did not occur naturally. Minerals have to be inorganic. In other words, they have to be made up of non-carbon material for the most part, or they have to come from non-biological processes. So, seashells are usually made up of either aragonite or calcite. Generally speaking, as a seashell, they're not considered a mineral. Once they've undergone some of the processes that take place during lithification, including diagenesis, which causes a recrystallization of the material, then it becomes a mineral. It has to be solid, can't be a liquid. So ice is technically a mineral when it occurs naturally, but water is not. It has to have an orderly internal structure. In other words, the atoms that make up the material have to be arranged in a particular pattern, a pattern that is repeatable. And it has to have a definite chemical structure. In other words, the chemistry of the material has to be the same time in and time out. So one of the most important minerals that we deal with is quartz. It's one of the more common ones. It has a very specific chemical formula, Si silicon O2, 2 oxygens, or silicon dioxide. Another mineral, one that's important for life and actually was worth more than gold for much of human history, is sodium chloride, or halite, aka salt. So let's go forth now and define what a rock is. A rock is a object that is made up of a mass of one or more minerals. So a mineral can be a rock, and a rock can be a mineral, but all rocks are not just one single mineral. They can be multiple minerals. So let's look at the composition of matter and see how we build this up. First and foremost, let's start with the idea of an element. Okay? Elements are the basic building blocks of minerals. There are something like 115, 119 now known elements, although only about 92 are naturally occurring. The rest we've had to make in colliders to create them simply because they are so unstable that they do not exist naturally for very long when they are actually formed. We basically recreate the conditions in exploding stars that will create those elements, but they don't last very long to begin with. So what's the basic building block of an element? Well, an element is an atom. That's the most basic building block of matter. It is the smallest portion of matter that cannot be subdivided any further without changing its properties. So it retains all the chemical characteristics of the material in general. So what is an atom made of? Well, if you think of the basic model you may have seen in school, elementary school or high school, you think of something that's got a bunch of little balls in one compact mass. surrounded by smaller balls flying around it. You have the nucleus of the atom, which is where 99.999% of the mass of the atom actually is located. And that is containing two primary particles, the proton and the neutron. A proton has what we call an atomic mass of 1, and it has a positive electrical charge, hence the name proton, because it's positive. A neutron has an atomic mass of 1, but it has no electrical charge, hence it's neutral. Now, why does this matter? Well, it matters because when we look at an element can be defined by the number of protons within it. So hydrogen has 1 proton, helium has 2, so forth and so on. But we can also identify isotopes of elements. One of the things is that there's something out there called the atomic mass number for elements. Every element has an atomic mass number. Now, the atomic mass number for, say, hydrogen, you would think might be 4, because hydrogen tends to be 2 protons and 2 neutrons. And if each one has an atomic mass unit of 1, 2 plus 2 is 4. When you actually look at the table, though, the atomic mass number for helium is slightly different than 4. And the reason for this is that there are other forms of helium that we call isotopes. And an isotope has a different number of neutrons. Same number of protons, but a different number of neutrons. So as long as the number of protons stay the same, the element stays the same. The number of neutrons change the physical mass of that atom and can have an effect on the overall atomic mass of that element on average. And we'll talk more about, having a hard time tonight. We'll talk more about isotopes here in just a little bit. Okay. Now, surrounding the atom is the electron cloud. The electrons surround the nucleus. They're made up of electrons, which for all intents and purposes are massless. They have 0 atomic mass, but they have a negative electrical charge. So in the ideal situation, you will have the same number of electrons orbiting the nucleus that you have protons in the nucleus. And this will create an electrically neutral atom because you'll have the same number of negative charges orbiting the same number of positive charges. Okay. Now, this is going to be here important here in just a moment, but just to review, atoms are made up of a nucleus, which is protons and neutrons, surrounded by a cloud of electrons. Now, here's the interesting thing about atoms. They are literally 99% empty space. All the mass is in a little point that is the nucleus, and there's a large cloud of the electrons around it. So, technically speaking, if you call somebody a great waste of empty space, you're being accurate, scientifically speaking. All right, so we have atoms. Well, now we want to get those atoms into what we call compounds or molecules. So we have to join the atoms together. How do we join them together? This is a process called bonding. And this is when a compound forms when 2 or more atoms join together. They can be the same atoms or 2 atoms of the same element, such as oxygen or nitrogen. Most of the air we breathe is made up of those 2 atoms, but in the form of N2 or O2. So 2 atoms of nitrogen joined together or 2 atoms of oxygen joined together. But we can also have other things like H2O, hydrogen with 2 oxygen, aka water. So one of the ways that we can do this is through what we call ionic bonding. The outer shell of electrons, it can be referred to as the valence electrons. Some atoms are willing to give up a valence electron. Some atoms are desperate to get a valence electron. And it basically falls to the number of electrons in that outermost shell. Now, once you get past helium, the outermost shell of any atom will hold up to 8 electrons. That's it, 8. So the ideal state for an atom is it wants its outermost shell to be completely full. So if you have an atom that has 7 electrons in that outer shell, it's going to be very, very desperate to grab one more electron. If you have an atom that has 1 electron in its outermost shell, it's going to be desperate to get rid of that one. So an anion is an atom that wants to fill in that shell and grab that one extra. So it's going to have a negative electrical charge, whereas a cation usually gives up electrons and it will have a positive electrical charge. Ionic compounds happen when you have a negative charge, a positive charge, they attract, and they neutralize each other. So for example, let's use salt, halite. Sodium has 1 electron in its outermost shell. Chlorine has 7 electrons in its outermost shell. Sodium wants to get rid of 1. Chlorine wants to gain 1. And they will easily do so, becoming a chlorine atom with a negative 1 electrical charge and a sodium atom with a positive electrical charge. In the right circumstances, usually in an aqueous solution or a water solution that has salt in it, as the water evaporates, the salt gets left behind, it gets into a high enough concentration where bonding can occur, and you will have sodium and chlorine bond together. And they will also form a pattern together that usually results in cubical structures, which is the crystalline structure of halite. So we can have atoms that are bonding through this simple change in charge, and then opposite charges attracting. Now, one thing to keep in mind about this is that size actually ends up mattering. Not your book, but a different book I happen to have can show you this. So, for example, at least I think it's in this one. Nope, this one doesn't show it. Dang it. Wrong book. Oh well. Certain atoms, when they become an ion, and that's what we call any electrically charged particle is an ion in general. Remember, anion for negative, cation for positive. They have a size, and they have a size basically because of what happens when you change the electrical charge. When you remove a electron from the orbital cloud, the atom will tend to shrink in size a little bit because you have a stronger positive charge pulling on the negative charge that's outside, so the atom shrinks down. Put an extra electrical charge in, and the atom gets a little bigger. You can swap out different elements of the same charge if they're close to the same size. So this comes to be important for some of the silicate minerals. So I mentioned last time olivine having a chemical formula that included iron and magnesium. Well, the reason for this is it turns out that the ions of iron and magnesium that are being placed within the structure through an ionic bond happen to be just about the same size. That's why they can swap in and out for each other. Now, another way that atoms can bond is what we call covalent bonding. This is a little bit different than the ionic in that you're not swapping out electrons. Instead, what's happening is an electron is being shared. So this is very common in the gaseous elements like hydrogen and oxygen and nitrogen. When 2 oxygen come together to form O2, there is an electron that is being shared. So it's bouncing back and forth between the two, and that's what bonds the two together. There are some other bonds out there that we should be aware of. One is metallic bonding, which is where the outer electron or electrons can be shared among all the atoms of the same element within the material. This happens to be one of the reasons why metals tend to be very good electrical conductors, is because they bond through metallic bonding. So they share their outer electrons which allow them to move freely through each other. Also creates some of the other properties potentially in terms of the way they are malleable. Now, you can have elements that are made up of one type of bond. You can have elements that are made up of two or even three types of bonds. There are some other types of bonds we're not going to get into. They get very, very detailed chemistry for that. We're not going to worry about them. They're also pretty rare, so we're going to stick with these three. Now, going back to what I said earlier about the number of neutrons creating an isotope, one of the things that this creates is, again, the mass number. Again, number of protons plus the number of neutrons equals the atomic mass number. But we have isotopes, different numbers of neutrons in different elements of the same atomic number, but they can have different numbers of neutrons. So like there's uranium 235 and uranium 237. The difference, uranium 237 has 2 more neutrons in it. Now, this is important to us because certain isotopes of elements are unstable, or what we call radioactive. And when we talk about geologic time, we'll delve more into this then. But basically, this is what causes this instability causes the elements to sometimes undergo a spontaneous change in the nucleus that can actually change the element from one element to another. So what's the structure of minerals? Well, an orderly array of atoms chemically bonded together form a particular crystal structure. Your book and the lab book go through a little bit on the crystal structures. I do not plan on really testing anybody on the crystal structures for a very good reason. There's a reason why good crystal structures are can be very expensive. Let me grab something. This is a piece of quartz, as you can see, hopefully see. It is a 6-sided chunk of crystal, and it has got its crystal form to it. It comes to a nice point and whatnot. It's not perfect. It's not equidimensional. It's kind of hard to see. There we go. It's not equidimensional. It isn't a perfect hexagon in terms of its cross section. All the sides are not equal. In order to grow a crystal, a large crystal, you need a couple of things. You need the material necessary to build the crystal that big. You need the space in order to build it. And you need the time to be able to build it. So a lot of times, really good crystals are rare and hard to find. So that's one of the reasons why the crystalline shape of minerals tend not to be very diagnostic. Now, there are a few exceptions to that, and we will talk about those, especially when we're dealing with igneous rocks. There's certain minerals that that can express themselves in the rock in a way that we can see some of what their crystalline shape might be and use that as a diagnostic feature. But generally speaking, in your day-to-day activities, you don't come across the crystalline structures of minerals that often. So I just wanted to cover that. There are a number of different types of crystalline structure. There's cubic, there's hexagonal, there's pentagonal. I mean, you get into all sorts. Now, generally speaking, compounds formed by ions, the internal arrangement are going to be primarily arranged based on the size and of the ions and the type of elements being bonded. However, we can see polymorphs in this. Now, polymorphs are 2 or more minerals that have the same chemical composition. I believe Hector was asking this last week. But they have a different crystalline structure. So I mentioned when we met about olivine and eclogite, diamond and graphite are also examples of this. So a transformation of one polymorph into another is what we call a phase change. What are some of the physical characteristics of minerals? Well, we've already talked about the crystalline structure. Again, that's That's the outward expression of the internal arrangement, but it's often interrupted because of competition for space. So it's not something we really focus on. Another one is luster. Might as well not put this down for a moment. Luster is an interesting characteristic. It is the characteristic of how light reflects off of a surface. Okay, so when we look at luster, we will define luster based on the way the light is bouncing off, the way it looks to us. So, got an old Fitbit band here. I don't know if anybody can see that. Now this is painted, but there's spots where the paint is rubbed off. Hopefully you can tell that what type of material this band is. And hopefully you would say it is metal because it actually has a magnetic end on it. So you can also see if this track spike that's stuck to it, that's metal. So a luster that is reflecting light, much like a metal reflects light, is what we call a metallic luster. If it doesn't look like metal, either shiny new metal or old dull metal, it's non-metallic. Quartz is a good example of non-metallic. Now, your textbook does get into the other lusters that are out there. A lot of them are classified as non-metallic. For the purposes of our labs, for the purposes of our testing, you are perfectly fine if you stick with metallic and non-metallic. However, if you want to delve into the depths of what are the other lusters, think about what it looks like in terms of the way the light is coming off of it. So for this, this would have what is called a vitreous luster because it looks glassy, which makes sense since quartz is a lot of glass, a lot of the primary material for glass. Whereas this piece right here, actually the front of this, might look more, let's see if I can get it, yeah, more resinous because it's a plastic. So the light looks like it's coming off of a plastic. You can have earthy, you can have dull, you can have silky, you can have satiny, you can have, you name it, literally pearly. You name the way you can classify the way light looks like it's coming off, you can name the luster that. That's why non-metallic is a good one. There's also color. Color is a very, very unreliable. Pure quartz, usually clear. A little bit of water, this could become milky. Expose it to a little radiation, it can become a gray-brown or smoky quartz. Add a little iron into it instead, and it becomes yellowish or citrine. A little magnesium, it becomes purple, so amethyst. So, you know, one material, multiple colors. And the reason for this is that it doesn't take a lot of a contaminant to change the color of the material. So you can have exotic coloration and inherent coloration. There are very few minerals that we, generally speaking, will use their color as a key diagnostic. A couple of them would be like azurite is azure blue, malachite is a vibrant green, sulfur is almost always yellow. So things of that nature. Many minerals actually will show a series of different colors because of possible contaminants within them. Another one is streak. Now, streak is very similar and related to color, but it's a bit different. You may have noticed that if you make things into smaller bits and pieces, the color kind of gets brighter or changes a little bit. What streak is the color form of the mineral when it's powdered. We usually test this on a streak plate, a piece of unglazed porcelain usually. You can get them in white. Streak plates are the most common. You can get black ones. And you rub the material on there and see what color it is. Now, this only works if the mineral is softer than the streak plate. If the mineral is harder than the streak plate, it won't leave a mark. But we can then see what the color is. So for an example, I don't know what's going to be in your kits yet, but if you have a mineral in there that's brassy or a brassy yellow to gold looking with metallic luster, if you run that across your streak plate, you will probably see that it'll have a black streak. That's pyrite or fool's gold. Streak is very, very important when we're dealing with minerals with a metallic luster. It's less important when we're dealing with the non-metallic minerals. Then we have hardness. Hardness is a measure of the resistance to scratching. The original hardness scale was done up by Moe and was based as a relative hardness scale. So what do we mean by relative hardness scale? Well, you're just putting things into relative order in terms of this will scratch that. So generally speaking, a good rule of thumb when you're doing this is something of the same hardness generally will not scratch something else of the same hardness. So two things that are equally hard should not scratch each other. Occasionally they will scratch each other. So if they don't scratch each other or they will scratch each other, good indicator that they are the same hardness. Anything else, the one that scratches is harder than the one that was scratched. Okay. Now, Mohs hardness scale, as hopefully you see in your book, has 10 levels to it, starting with the softest: talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, corundum, topaz, diamond. Okay, those are the 10 naturally occurring materials in terms of their hardness, from the softest to the hardest. There's a mnemonic to memorize it. I'll run it by you real quick. Whether you use it or not, up to you. Tall girls can flirt and other queer things can do. Again, tall girls can flirt and other queer things can do. Tall talc, girls gypsum, can calcite, flirt, fluorite, and apatite, other orthoclase, queer quartz, things topaz, can corundum, do diamond. So remember, so it's just talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, diamond. Your hardness kit, which you should have a hardness kit in your lab kit, I hope. It will have everything except diamond. Nobody gets diamond. Now, you can keep a few things around you if you're ever interested in knowing what the hardness of something is and you're out on a hike or just out and about. Your fingernail, as long as it's not an acrylic nail, it has a hardness generally of about 2.5. A copper penny, if you can find a solid copper penny, not a copper plated penny. So you're looking for a penny that's usually 1978 or older. That has a hardness of about 3.5. A wire nail, like a finishing nail, has a hardness of about 4.5. Your knife blade or a piece of glass is roughly about 5.5, and a streak plate is about 6.5. Masonry drill bits will come in somewhere usually around 8.5 in that ballpark. Hardness can be very important to us for identifying things. It's hard to test if the sample size is small, though. Another form of property that we want to be keeping in mind is cleavage. Cleavage is the tendency to break along planes of weakness within the bonding itself. So it has to do with the chemical structure of the material. There are preferred planes that the material will break on. Now, one of the ways you look for cleavage, the way I like to say is, like this is clear, is you want to look for sides that parallel it, for one thing. So you would think this quartz crystal, well, those two sides parallel, these two sides parallel, these two sides parallel. You would think maybe that has 3 directions of cleavage. But it doesn't. There are some other things you want to look for, especially in a clear sample like this. you should be able to see reflections of those same planes within the material when it's clear. You don't see that with this material. In fact, actually, if you look at the end of it, which you're not going to be able to see too well because of the lighting, the end of it looks like broken glass instead. It has these curving structures to it. Like there's a piece right here where it's broken, kind of hard to see. You're getting a reflection off of it. That's a curved surface reflection. You would, in a good piece of clear material with cleavages in it, you would expect to see planes of breaks that parallel those parallel planes all the way through it, or part way through it in some areas, depending on how good the sample is. So that's one way to look at it, though. Now, another way is if I have this as broken, and I will see like a stair-step arrangement where I see other planes of the same plane, and they all reflect back at me. That's another way to do it. Another thing is, it's kind of hard to see on this one. I don't know if I can get you to see it or not. Yeah, kind of. Kind of see how I've got almost like ridges. You can feel them on here, but you can kind of see this ribbed texture on it. Cleavage planes tend not to have that. They tend to be fairly smooth and smoother to the touch. So that's another clue that you're not dealing with cleavage in this particular sample. But another way to think of it also is the numbers and types of cleavages that are out there. There's one direction of cleavage, and this is very common in like the mica minerals where they will peel off in large sheets. There's two directions of cleavage, and they can either be at right angles, so 90-degree angle, or not at right angles, say like a 120-degree angle. This is actually very common. The plagioclases tend to have 90-degree angles, where a mineral like hornblende, which is part of the the amphibolite group, has angles of 120 and 60, which gives it a very distinctive diamond shape and cross-section in igneous rocks. You can have three directions of cleavage. They will either be at 90 degrees or not at 90 degrees. Think of a box, a cube, for the at 90, and a box that you've kind of pushed over in one direction for the not at 90. And then you can have four directions of cleavage. And that's basically it. So you this wouldn't be three directions of cleavage in radial. It would be a three-direction cleavage would be 3, 3, and then 3. Or 1, 1, and 1. Sort of like, again, forming a cube. Instead, quartz has what we call fracture. Fracture is the irregular breaking of the material. It has generally two types. One is irregular. The best way I can explain irregular is think of a broken brick. Or it can have conchoidal fracture. Conchoidal fracture is what happens with quartz. It breaks like glass. So it has those curving surfaces like you see in broken glass from time to time. Another property is what we call specific gravity. Now, specific gravity is the ratio of the weight of the mineral to an equal volume of water. There are a couple of different ways to measure it. You're in the lab, you're going to be doing, there is actually a question based on that, so you'll read that in there. But generally speaking, it's basically what is the density of the material in relationship to the density of water. Most rocks have a density somewhere between 2.7 and 3 grams per cubic centimeter. Water is 1 gram per cubic centimeter. So you can tell a lot by picking up a rock and just hefting it in your hand. If it feels really heavy for its size, odds are it's going to have a lot of metal elements within it, and therefore that gives you a clue to what it could be. There are some other properties that minerals can have, taste being one. Halite, salt, has the property of taste. It tastes salty. There are some other minerals that have other taste. Glauconite is very bitter. There's also feel. Some minerals have a feel to them. Chlorite is a mineral. It's very similar to mica, but it feels soapy to the touch. Same with talc. They feel like fresh soap to the touch. They're slippery almost. They can have a smell. Sulfur is a good example of that. If you get a piece of sulfur, you're going to smell that sulfur. If you've handled a piece of sulfur, you're going to smell sulfur for the rest of the day, practically. Some of them have a malleability. In other words, they can bend a little bit and hold their shape, or they can be elastic, in which you bend them and it will spring back. You can also have magnetism. There's really only one mineral with the property of magnetism. You can have double refraction. This is a key one in calcite, where because of the way light travels through it, if you put a piece of clear calcite down on a page of text, you'll actually see the text twice. So it's called double refraction. Calcite has another special property called effervescence, in which it reacts with dilute acid placed on its surface. It bubbles. All right, so now we're going to go through and talk about the minerals in general. Now, here's where the daunting part comes in. Generally speaking, there are over 4,000 known minerals in the world. Yeah, 4,000. Here's where the good part comes in. In terms of common minerals, there's only a couple of dozen common minerals. In terms of the rock-forming minerals, it's only a few dozen. Generally speaking, the crust of the earth is made up of a handful of elements, and that actually controls what types of minerals you're going to have. So if we look at the crust, the makeup of the crust in terms of its chemical composition, by weight, we estimate the weight. The number one element in the Earth's crust is oxygen at 46.6% of the crust. That's closely followed by silicon at 27.7%. Obviously, the most common minerals that are going to be out there are going to be based on that combination of oxygen and silicon. Then we have aluminum, which makes up 8.1% of the crust. Sidebar note here, you have people that tell you that autism is caused by aluminum in vaccines. Couldn't be further from the truth. Aluminum is the most common metal on the Earth's surface. You can't get away from it. Iron is the next most common element at about 5%. Then you have calcium, which is at about 3.6%. Sodium, which is at about 2.8%. Potassium, which is about 2.6%. And then magnesium, which is about 2.1%. And that's 98%, a little over 98% of the Earth's crust by weight, which means the other 84 naturally occurring elements make up the less than 2% of the Earth's crust. So, based on that, again, we can say that silicates are going to be the most common mineral group, and lo and behold, they are. Now, silicates are built on what we call the silicate tetrahedron. This is a pyramidal structure. It's a four-sided pyramid. So imagine three corners on the bottom and one corner on top, kind of like a caltrop in shape. So, it's going to be a diamond shape, that diamond shape on the bottom, or triangular shape on the bottom, and all four sides are going to be triangular shapes. So it forms a pyramid, but only four sides. Three sides around plus the bottom, four-sided pyramid. Now, that molecule happens to end up with a -4 charge. So it will join up with other materials to try to neutralize itself. And this creates the other types of silicates. So basically, the way those tetrahedra join together is going to control a lot about those silicates. And there's basically four ways that those tetrahedra will join up. The first is they don't. They are isolated tetrahedron. Then you can have a single or double chain. So it's a chain one way, one chain or two chains. Actually, I can show you. There we go. So the isolated like this, which is olivine, single chain, which is usually a pyroxene, double chain, which is going to be your amphibolite group. Then you can have a sheet. Now, a sheet will extend off in any direction, literally infinitely, as long as it has material. So those are going to be your micas. And then you have the three-dimensional structure, which is going to be like feldspar and quartz. Okay, we're going to talk about these in just a bit more. But basically, the negative structures are neutralized by the inclusion of metallic cations that bond them together. Ions of the same size can move freely or substitute freely. That's why, as you'll see with some of these chemical formulas, they have a couple of different ions that can swap in and out. In some cases, ions that interchange don't even have to have the exact same electrical charge. That's a little more fancy than we're going to get into with discussing this. Now, generally speaking, we can classify the silicates as being two primary types. There's the ferromagnesium silicates, aka the dark silicates. These are ones that are going to tend to have iron and magnesium in them. And we have the non-ferromagnesium or the felsic silicates. These are going to tend to have different elements in them, namely sodium and potassium. So if we look at it, we're going to start with the dark silicates, the ferromagnesium silicates. The first of these is olivine. Olivine is a high temperature mineral. In fact, olivine is one of the first minerals to actually form out of molten rock when it's cooling down. It tends to form small rounded crystals. They're individual tetrahedron that are bonded together by mixtures of iron and magnesium to each other. Olivine is olive green, has a similar hardness to quartz, and also has a conchoidal fracture to it. But it's green, and it's usually a little bit denser. So that's one of the ways we can tell it apart. This next group are the pyroxenes, or the single chain of silicates. The most common member of this is a mineral called augite. Again, we have tetrahedron that are arranged in a single chain, and they're bounded by iron and magnesium minerals, or iron and magnesium elements to bind the chains together. We do see cleavage present. It tends to be two angles of cleavage at 90 degrees. Then we have the amphibolite group, or the amphibole group. The most common member of that is a mineral called hornblende. The tetrahedron, again, are double chained, and we do see cleavage present. For hornblende, it's exactly 120 and 60 degrees. So they form this kind of a rhomboidal diamond shape in cross section. So if you see and they're almost always black. They sometimes aren't, but almost always are black. So if you see what looks like a black kind of funky little diamond in a rock, that is going to be hornblende more often than not. Then we have biotite, where the tetrahedron are arranged in a sheet, and they are bounded together by the individual sheets are bonded together with metallic ions in between. These tend to have excellent cleavage because the sheets will just peel off of the other layer of ions. Then we have the non-ferromagnesium, or the light silicates. The first one of these we'll talk about is muscovite. Very, very similar to biotite. The main difference is biotite tends to be a dark brown to black in color. Muscovite tends to be clear to almost silver in color. Sometimes a little smoky depending on how thick it is. Feldspars are another group that we need to talk about. Feldspars actually are the most common silicate mineral out there. They basically are a three-dimensional framework of the silicate tetrahedron. They are almost always two angles of cleavage that are just about at or right at 90 degrees. They tend to have two different varieties of feldspars in general. One is the potassium feldspars. These tend to be light colored to red or pink in nature. This is because they have potassium within them. They don't have the main minerals or the main elements of the other feldspars in them. Then you have the plagioclase feldspars. The plagioclase feldspars fall on a spectrum of having either 100% sodium or 100% calcite or calcium, or something in between. Some examples of this are the minerals anorthosite, albite, labradorite, and a few others. Some key characteristics of the plagioclase feldspars is they show an iridescence or a play of colors, what we call pleochromism. If you find a surface like this and you move it back and forth, you see like an iridescent blue sheen coming off the surface, especially in sunlight. That is a very strong indicator that you're dealing with a plagioclase feldspar. Plagioclase feldspars will also have striations on their surfaces. They literally look like laser straight lines across the surface, all going in the same direction. You can try to run your finger on them, you don't feel them, but they're actually an expression of the crystal itself in the way the mineral is formed in its crystalline structure. And then, of course, we have quartz. Three-dimensional network of almost pure silicon dioxide. Then we have another class of minerals that we're not going to get into too much. We'll talk about them in general, and that's the clays. Clays have a sheet-like structure, but they literally are so complex. We tend to use it as a catch-all. As we'll see later on, it can also refer to just a size issue. But clays, the minerals of clays, are very difficult to tell apart. They're all the product of chemical weathering, as we'll talk about in about 3 chapters. But the only way to really tell them apart, for the most part, is X-ray spectroscopy. We're not going to be doing that in the lab, so we don't have to worry about it. There's some other important groups we should touch on in general, such as the oxides. These are going to be minerals that are made up of an oxide. So like iron oxide, rust is technically a mineral, but iron oxide can be in the form of magnetite, ilmenite, hematite, or you can have an aluminum oxide, which is corundum. We have the sulfides, we have sulfates, we have the native elements, gold, copper, silver would be the ones for the native ones. We have carbonates, which are made up of usually calcium and carbonate, so CaCO3, so calcium plus a carbon plus 3 oxygen. There's some other carbonates out there as well, but calcite is the most common one. The hydroxides, as well as the phosphates. Generally speaking, let's go back for a moment to the carbonates. The 2 most common types of the carbonates are calcium carbonate, calcite, or calcium magnesium carbonate, dolomite. Very key question for you guys to be able to answer at some point on a test is, how do you tell the difference between calcite and dolomite? Well, it's actually very simple. Both will react with acid, but, very important but, calcite reacts readily to the acid. All you got to do is drop it on there. Dolomite, you have to powder the surface up first. You have to crush it before it will react with the acid strongly. So that's a good way to know the difference between the two. Then we have minerals that we call the evaporites. The evaporites are minerals that will dissolve in water and then precipitate out when the water goes away. Think about when you were a kid and you lost a tooth. What's one of the things your parents gave you besides money when you lost a tooth? Odds are they gave you a cup of hot salt water. The idea being is rinse the mouth, try to help get the blood out of your mouth and as well stop the bleeding. Now, most people don't use up all that hot salt water. They leave some in the cup. They leave the cup on the sink. What happens a couple of days later? You come back, the water's gone, it's evaporated. The salt is still there. The salt precipitated out. When the water evaporated, the salt was left behind, hence it being called an evaporite. Salt is one of the primary evaporites that we deal with. Gypsum is the second one. Now, as I said, wall boards here are gypsum. Okay, they're important non-metallic resources. Now, many non-silicates can also be economic value. Hematite, magnetite, ilmenite, good sources of iron. Sphalerite is a good source of zinc. Galena is a source of lead. So with that, I'm going to go ahead and cut it off here. Again, please read Chapter 3 as well as Lab 1, and we'll talk about that if you can. If not, save Lab 1 for reading before Wednesday, and I will talk to you guys later. Have a good one.